Insert your independent variable in the upper box and your independent variable in the lower box. Click on Statistics and this box will pop up. Then click on all the important features that should be shown in your results. Note here that there is a tiny box for correlation, which will show correlation analysis within your linear regression analysis. Click on Continue. Then, to take you back to this initial box, you have to click on Plots to analyze the residuals of the estimation. This box is going to pop up. This box to show you the residual values. The standardized predicted values should be moved into the lower box. The standardized residual values here should be moved into the upper box. Remember to click on histogram and normal probability plot. Then click on Continue. To take you back to the initial box, then you click on OK. The results will be shown in the output page. As you can see, there is a box for correlation within linear regression analysis. But if you want to carry out correlation separately on Spss and you've imported your data, click on Analyze, click on Correlate by Variate. It will bring up this tiny box. Then move your variables to the right hand side. Click on Parsing, click on the test of significance, and the last one, click on OK. Now we have to interpret the result of the linear regression analysis. The result shows us that the coefficient of the independent variable is 0.706 and it is shown in the result here. You know that our independent variable in this exercise is GDP, and the coefficient for GDP is 0.706. That is the estimate of the independent variable x is 0.706. The constant value is minus 184.078 and it is shown above the independent variable. This is the intercept. It is also called the constant. What do these figures mean? The intercept, which is minus 184.0.08, is the value that y will take when x is 0. That is, when there is no increase at all in income, consumption expenditure, the rate of change in consumption expenditure will be minus 184.08. What does 0.706 tell us? It tells us that when there is 1 unit change in income, consumption expenditure will increase by 0.706. In reality, it means that when there is an increase of $1 in disposable income, it will cause consumption expenditure to increase by 76. As you can see, 0.706, which is the coefficient of it, is approximately 76. Now let's talk about R square. In our results, R square is 0.998 and it is shown here. This is R square. R square of 0.998 in value means that 99% of the variation in consumption expenditure is explained by the change in the independent variable, that is GDP. The value of R square should be multiplied by 100 to turn it into percentage. Pearson correlation in these results tells us that the correlation between the two variables is very significant. For you to check the value of correlation between your variables, check where your dependent variable is crossed with your independent variable. The figure in between them is the correlation. As I already mentioned, a correlation coefficient that is closer to 1 tells us that there is a strong positive relationship between the variables. The Pearson correlation coefficient of 0.999 is very close to 1, and it shows us that there is a strong positive relationship between consumption expenditure and disposable income. Now let's talk about goodness of fit measure. How do you know that the model is a good fitting model and that it can be used for making predictions accurately? When your R square is closer to 1, it implies that your model is a good fitting model. But when your R square is closer to 0, it tells you that your model is a poor fitting model. However, a low R square might be showing you that some important independent variables are missing in your model and that your model cannot be used for making predictions accurately. However, a low R square still explains the relationship between your variables, but your model cannot be used for making predictions. Another way to tell if your model is a good fitting model is to check the value of adjusted R square. Adjusted R square is shown in our results right beside R square. What is the function of adjusted R square? I'm going to explain it. When you add more variables to your model, it will increase the value of R square automatically, regardless of the true impact of the additional variables. In order to correct that mistake, the adjusted R square will adjust the value of R square. Therefore, it is more advisable to use adjusted R square. Now let's talk about residuals. The estimates of the parameter will be used for making predictions, but your predictions usually does not correspond to reality. Your predictions cannot be completely accurate. The difference between your prediction and reality is the residual. In order for you to know if your model will make a moderately accurate prediction, you have to check the analysis that was carried out on the residuals. These are the results for the analysis of the residuals. The scatter plot here and the histogram. The scatter plot shows that the residual is randomly distributed. That is, the dots on the scatter plots are randomly distributed. They do not have a particular pattern. This shows us that there is no autocorrelation between the residuals, and this complies with the assumption of OLS. We're going to talk about the assumptions of OLS in another video. The histogram shows us that the mean value of the residuals is 0. That is another assumption of OLS, and this histogram shows that that assumption has been met. If the mean of your residuals is 0, that shows you that your model is a good fitting model. Now we are at the stage of hypothesis testing. How do you know if the relationship between your variables is significant? And how do you know which hypothesis to reject and which hypothesis to accept? You can simply do that by checking the significance value within your coefficients table. This is the column for significance value. This is the t value just before the significance value. Now, the significance value for your independent variable is within the same row with your independent variable here. And for this exercise, the significance value for GDP is 0.000. And remember that we are using an alpha value of 0.05. Since 0.000 is less than 0.05, that is the alpha value, we are going to reject the null hypothesis that says that there is no relationship between the variables, or that the relationship between them is not significant. And we are going to accept the alternative hypothesis. Another way by which you can check the significance level between your variables is to check the t statistics in the results. This is the t statistics for your independent variable, 90.247. Then we compare it with t critical value that will be taken from the t table. You have to know what your degree of freedom is. This is where you pick the value of degree of freedom, the total, which is 14 in this exercise. Then you're going to use it on the t table. This is degree of freedom column. We're going to look for 14 and trace it to find what the value of t critical will be under 0.05, that is our alpha value. Alpha value is 0.05. Check what that value, the t critical value is between the degree of freedom of 14 and 0.05. The value shows us 2.145. Then you compare 2.145 with t statistics value. If t statistics is larger than t critical value, we are going to reject the null hypothesis. In this case, t statistics of 90.247 is greater than the t critical value of 2.145. Therefore, we're going to reject the null hypothesis and conclude that the relationship between consumption expenditure and disposable income is linear and it is significant. Let us assume that there is a belief that an increase of $1 in income will cause consumption expenditure to increase by 1. How do we test this new hypothesis? Remember that our analysis shows us that beta coefficient is 0.706. That is, an increase of $1 in income will cause consumption expenditure to increase by a value that is greater than 0 but less than 1. And our estimation, our analysis gives us a value of 0.706. Now, we have another hypothesis that is saying that consumption expenditure will increase by 1, which is opposed to the initial hypothesis. We're going to take the difference between the initial hypothesis and the new hypothesis and divide it by standard error of beta 2, that is the standard error of